Good morning, everybody. The first speaker today is Ilia Zarkov from Kansas State University, who will talk about Lagrangian SYZ fibrations.
All right. Thanks to the organizers, Xavier and Krieg, wonderful talks. I'll try to do my best not to maintain the quality. So this is a joint work with Cheuk Yu Mak, Diego Matessi and H. The two of them are here. Cheuk Yu Mak is going to speak after me about the technical details. I'll just announce the main result and give strategy how we're going to prove it. So it's starting with the integral affine manifold B. Manifold. So D is a discriminant here, and I'm gonna use the words very simple singularity, because the word simple was used by Gross and Ziebert, and that's our word actually simpler than theirs, so it's very simple. And I'll explain what it is. And the goal is to kind of orthogonal to what Gross and Ziebert are doing. So they're trying to build like a whole holomorphic family, which has this base, and we are trying to build a symplectic manifold with that base, which should be easier in the sense that symplectic geometry is much more flexible to this. And then you will see there are a lot of possibilities here. So let me explain what's this word simple singularity means. So B is a topological manifold, and the D inside of it is a regular CW complex of codimension 2. So it consists of a bunch of strata, and the neighborhood of each strata delta. So neighborhood of each strata of delta looks like the following thing. So it's the let me call it delta itself cross y cross another y. Let me call it y check. And the y is what usually people call by y is this tropical hyperplane inside Rn. So it's an n-1 dimensional polyhedral complex. We're only topological, so we don't care much about straightness. And the y check is the same thing, only let's say this is Rk. So it's a k-1 dimensional thing. And let's say let's dimension d. So this is Rd. And K. Yeah, so the typical picture would be something like you have a plane in R3, and inside the plane you would have something like that. So that's the example. We have the two embeddings of or actually one embedding from the smooth part B minus D into B. And then being integral affine manifold outside D means that we have two lattices here, so lambda and lambda check. So this is the integral lattice inside the tangent space, B minus D. Integral lattice. And this is, of course, in a dual space, so it's a cotangent integral lattice. D. And then what we're gonna do, we're gonna look at this is the next data which involves to every stratum delta, to every delta in D, we associate two simplices. So delta is inside this integral lattice. So we push it forward to the stratum delta, and then we see that what's left of lambda is just the invariant sublattice in it. So it's going to be a simplex inside the invariant sublattice, and the same thing about the delta check. So it's inside the invariant cotangent sublattice. And then, so this is a K simplex, so this is N simplex. And this is a K simplex. And we want them to be orthogonal. And to these two simplices, we associate the monodromy yeah, first of all, there is a condition of compatibility. So if you have a stratum delta, and then you have a smaller stratum delta, this is delta prime, this is delta, smaller stratum, so we have delta substratum of the prime. Then we have inclusions, delta is a delta check is a subphase of delta, and so is delta check, delta prime check. And then we associate the monodromy. So the monodromy is around the largest stratum. So the largest stratum, so largest delta, largest stratum means that it's codimension 2 thing. So then both of this delta and delta check have to be intervals. So delta is, let's call it E, an interval, and delta check is another interval F. Then the monodromy around this stratum, so there's a monodromy around it, is identity plus E tensor F. So in terms of the metrics, it is an identity matrix, except in one place you have one here.
Can we move this white thing?
The white thing.
Because
Can we move the white thing?
Yes.
And there's one more condition. I mean, the monodromy itself is not enough. So there, something about we also want this, well, let me call it radiance free. Namely, that like for instance in focus, if you make a cut here and then you do your change of coordinates, you come back, you do not, have any shifts. So no shifts, only the, the bending of the tangential directions. All right. So there are other couple of conditions on the smoothness of the discriminant. So let me say, since now we have this strata actually lying inside this invariant subspace, let's call it. So this, let's call it pi number of this, let's call it like reals. This is B invariant. So this is an invariant subspace which does not have any monodromy. So this actually has itself the integral affine structure. So integral affine structure. And so does the quotient. But inside here, now we can talk about smoothness. So far it was topological manifold. Now we can talk about smoothness. So inside of this thing lies our delta. This is delta. This is B invariant inside the B. So we want it to be two conditions for the smoothness and transversality. So first of all, there is so the slice delta itself has to be transversal to the little delta. And optimal transport, I believe, supports that statement. So it's quite possible that's actually going to happen in a true Mondrian error base. So far no contradiction. And we want it to be smooth. So this delta is a graph of some function B invariant mod delta into delta, smooth function.
I don't think I understand where these simplices live. Where do they live? What's so that's a lattice.
That's a lattice. So
Yes,
so they live in this in a vector of space spanned by that lattice, but they are integral there. So this is why they live like in a lattice.
It's a tangent lattice, so you can move them around.
It's a
But
tangent.
the simplex can't live in the lattice, right?
All right,
Stage,
okay.
vertices live in the lattice.
But vertices are integral, and moreover, I want them to be unimodulus. I didn't say that. So it's a unimodulus. So each of this space has an integral structure because it sort of comes from the integral lattice, and the simplex is a unimodulus simplex in that tangent space.
And then when you draw this picture, you're doing like parallel.
Transversality, yeah. So I'm kind of So it's kind of move. So this simplexes they're kind of moving. They're not in a base. They're in a tangent space to the base. I can move them. And the transversality condition, of course, it's tangential.
So when you draw it like that, it's not a subset of the.
It's not a
plane.
subset. It's a subset of the tangent space. Yeah, of the tangent space. Yeah. So it's kind of moves. If I move a point, to simplify, it's sort of it doesn't have any origin or anything. So it's unimodular. That actually what differs from the Gross-Hilbert thing. So they want a larger class of simplices elementary. And they also have complete intersections. So, but I'm gonna just a very simple one. So this is smooth and transversal to the thing, and there is one more technical condition which we kind of couldn't avoid dealing with. If you restrict your discriminant to just this to this, so restrict discriminant near delta restricted to this subspace spanned by delta. Then you're going to see this kind of picture, this Y fan over there. And the condition on a Y fan is the following. So you have inside of this delta, inside of this space spanned by delta, there is a Y fan. That's what the discriminant looks like. And then also there is the simplex delta, which is a floating, but I'm going to draw it inside. And there are two conditions, which one is this tangent fan. Let me call it F to be the tangent fan, which is this straight thing. So the simplex, so the discriminant itself may bend, and I'll explain what's allowed for the bending. But there is a well-defined tangent directions here. And then the condition, this is now an ordinary polyhedral fan inside integral space. So, and the condition is that this fan F is what we call uniformly transversal. To delta. And instead of explaining, writing what's the definition, let me just give a picture. So this is your delta. Uniformly transversal means that it remains transversal whatever I move my delta, as long as the vertex is inside the simplex. So for instance, this one, no matter where I move my vertex inside the simplex, I remain transversal. So, and it's bijective thing. So every fan, every cone in a fan corresponds to some phase. So let's call this tau, and this is f tau. So there is a order reversing bijection between cones in the fan and the simplexes, faces of the simplex. And whenever I move, the corresponding fan intersect only its own dual face. So for instance, this is not this is transversal, but that's not uniformly transversal, because I can imagine that I can move it over here, for instance, and then I have wrong intersections. So this is actually a very rare condition. Like if you have an arbitrary polytope, it almost never happens. The arbitrary polytope never has uniformly transversal, but simplex always does.
And it's not only the one sort of a normal fan.
No, there's no normal thing, first of all. But if you're asking if that is uniformly transversal, I would say no. So it has to be like literally inside the thing. So this is good, and this is not good.
Why no on the right hand side? I can see.
It's. I want anyway. The point is that if I move this vertex into the opposite plane, this ray has to lie in the interior of that cone. That's the condition. I'm not sure how optimal transport support this. Probably it's not going to. I have a feeling that in optimal transport, the neighborhood would look like a cuspidal thing. So in a true Monge-Ampere solution, so that probably is not right. But this is we use that statement to we needed that. And then another condition that also this it's almost linear. So linear to all orders. at the vertex. So here we can wiggle this guy. It's okay. We will be able, and Cheuk Yu probably will say something how we wiggle it. I'm not sure if he has time, but we cannot wiggle it like arbitrarily to arbitrary orders here. So we have to stay like to all the orders of the. I mean, the wiggling here has to die like to all orders. I don't know. That's again maybe technical, but we couldn't get rid of it. Okay, and now. Doing good in time. Now let me state the theorem. So there exists a M mapped to be a Lagrangian fibration so there are two statements here. So M is symplectic manifold, and the map to be which agrees with the tautological one. So you take the cotangent space to the B minus D, you mod it out by the lattice, how called lambda check. So this is a torus, cotangent torus bundle over the open part of B, and then of course it maps to the B mod D, to the B minus D. So this is the tautological one, and then the statement that we can actually compactify it over the discriminant, which is hopeless to do in complex terms. If you take the tautological tangent vibration, you cannot compactify it to a complex manifold. Okay, I think I'm done with my talk, roughly speaking, and then stated the main result. But I have 40 minutes more, so I'm going to explain how we approach it. Because this is not just an existence theorem, it's actually better in the sense that we actually give a construction. So we have some control on what we can say about this vibration. Like, for instance, we can study, what's the singular fibers are, and, lots of other things. Yeah. Questions? Yeah.
Let me make a comment that I know you're not going to make, but you can generalize from the special simplex to a more general synthesis by simply an entire cover of the vibration.
Yeah. Except that it's not going to be a manifold. If the delta check is not a unimodular simplex, it's not a manifold. It's not manifold. If delta is not a simplex, not a unimodular thing, that's okay. But we need that to be to do the manifold. We need that to be a unimodular.
So you're saying all fibers are Lagrangian or only the fibers over E?
Oh, I mean, they're singular, well, in some sense, singular fibers.
Okay, so
But they are made of the of the Lagrangian components. Every fiber has a stratification whose strata are Lagrangian. I mean, you have singularities, of course, right? So
but M itself does not have singularity.
M is smooth, yes. I'm not claiming, by the way, the map is smooth.
Do you have control of the singularities of the special fibers? They are
Yeah.
somehow classified.
Well, not. It depends. So you'll see. So, but we have some control on that. I mean, it depends on how good you are in computing skeletons.
So there is kind
Any other questions? We did compute some of them, so I'll show. If I have time, I'll show some of them.
Yes, the master computing skeleton.
Huh?
He did some GG skeleton computation.
No, but it's hard.
In 3 dimensions, this recovers exactly the Matessi Cosmonian.
They have codimension. They have thickening. This is actually better. So, okay, let me actually say a couple of words. So I'm going to concentrate mostly on the local models. Also. Local model. And local model, I'm going to say of type KDN. Remember, this is where my delta check is k-dimensional. This is my delta n-dimensional, and n is my stratum. Sorry, D is my stratum delta. So, okay, so what's known before? Of course, so n equals 0 or k equals 0, no singularity. No no strata, actually, nothing to talk about singularity. But there is Arnaud-Liouville result. Liouville said that if you have a base, smooth base, there is a unique M and a unique map M to B, which is a Lagrangian fibration. Next example, maybe famous focus case. So we have the base, which is well been appearing a lot here. So you have a plane, and you have a monodromy is. I'm going to write it my way. Sorry, I'm going to write one top right, bottom left, and then the result is that there exists a unique symplectic manifold. Symplectic manifold, unique symplectic M, but the maps are not unique. So there are actually many different fibrations. So from M to B, and they are classified. The smooth one, the smooth maps are classified by so-called M-Dock invariant.
These are the different things.
Huh? Different thing? And of course, in high dimension, this becomes, you'll see that there are lots of flexibility. But let me mention, of course, there are a lot of people work here. I should mention, right? So there is, of course, the case of n equals 1 was done by the n equals 1, NEK. This is Castana Bernard. Matessi. So they've done it. They also done some work for the so-called k equals 1, n equals 2. This is negative vertex in Mark-Gross classification. The work somehow stuck to this thing. Vertex. So what these guys did, they kind of so that's a picture which I was trying to draw. So you have a two-dimensional invariant plane, and then you have the plane here. They couldn't do the fibration all the way in codimension 2, but they kind of had to thicken it a little bit. But then Mark Gross actually pointed us. This is where the starting point was. So there is a paper of Evans-Maury, which does this. Evans-Maury. They actually do it in this case. They actually do it all the way to the dimension 2. And we actually, so this is the source of our inspiration. The idea is to kind of construct the fibration in somehow far away from the origin, and then just take the Liouville flow. Take the cone that flow. The vibration from the Liouville bound. From the, well, it's called DM. This is also not good. Yeah. Questions?
What are delta in this example?
Okay. In this one, in the negative vertex, so the delta is maybe I'll draw this blue. Delta is a triangle. So delta is this one. This is delta. It looks like delta.
Same plane as that.
Same plane as delta is an invariant plane, and delta check. You kind of don't see delta check lives in a dual space, but sort of you can imagine it's kind of interval. Delta check.
So when you write a formula like this, can you write this formula for like one more example? K equals 1.
This
K
formula?
equals 2, yes. So that I can,
Well, I'm just describing the monodromy around the larger strata. If you want to do all the monodromy around, for instance, here, you would have a 3 by 3 matrix, and each strata would have a 1 in a.
I'm just trying to understand why you represent this data as a simplex. Like, why isn't it just some vectors or something? Why is this simplex? I don't know. It seems like there is a smart representation here. Because here, for example,
Yeah.
when you write delta equals E, that's
Yeah.
also not like a.
Yes, yeah, but this is just a
Why
monodromy
write it
around.
down?
Okay, so around this strata, the delta is just the interval, and this is all I need to describe the monodromy. I'll just need the smallest possible delta.
I suppose in this
Here, if you want to describe all the monodromy in this neighborhood here, there is the delta like that, there is a delta like that, and there is well, maybe tau. So tau 1, tau 2, and tau 3. So you have 3 different, and then you combine them into metrics. Each one of them would be in a form 1 somewhere, and that 1 would, here, here, or there. So this is this 3 things. Actually, not true. It's here. It's always 0 here. So it's 1 here. Well, so it's a star here. So it's in this form. The sum of these two has to be equal to the third one, or maybe that around. I have to think. One of the two.
Now, what happened to the positive vertex?
The positive vertex. Okay. Let's do the positive vertex. So now the delta is the interval and delta check is a triangle. For another example, maybe k equals 2, n equals 1. So this is called the positive vertex. So here is the delta is the interval, and delta check is a triangle. But what we're gonna see, we're actually gonna see the normal fan to the delta check. No, it's not good. But what we're gonna see, actually, we're gonna not see the delta check, we're gonna see the normal fan to delta check, which is in our space. And the picture looks like this. So this is your most singular point. There are 3 flaps like that. And the discriminant the shape of the discriminant is still this trivariant graph. And the delta is kind of lives in this invariant plane, which is so delta kind of lives here. So this is delta. And the normal fan which you see in the quotient, you can project this thing. You see just a standard tropical fan, and this is a normal fan to delta check. So let's prove. So I'm going to do this local case only. So
What is there's something called singularities of less single time.
well, it's more special. That's what I'm saying. So they have much more larger class of singularities, but that's a particular.
When you say larger class, you mean like even kind of monodromy wise, like.
Yeah, I mean they don't have to have like only, for instance, 2 simplices. So even if they have 2 simplices, you can make them to be not necessarily unimodular, elementary, right? That's what we call them, which are mentioned. So no vertices out except the vertices, no lattice points.
2 simplices are still fine, they all standard.
Hmm?
Like this form. 2 simplices are always
Two
is always
elementary and the
three
unimodular
dimensions,
for 2 simplices, but in dimension 3 you might have some non-unimodular simplices.
ambient space has to be dimension 4.
Yeah. And also another, so you might have more than 1 pair of simplices, you might have several pairs. And this kind of, so this is kind of correspond to the hypersurface, and you have complete intersection, then you might have several pairs of We'll probably do it at some point, but so far.
Can I ask you one more question? Probably a stupid question about the second image there. So when you had a triangle around your trivalent, then I understood that you like each edge in the triangle corresponded to the holonomy around one of these.
Yeah, same thing here.
So, but on the right hand side there's just an interval. Delta is just an interval.
Yeah, but still there is the array here, and what's the so it's still going to be 3 by 3 matrix, but the difference from this one up to switch blue and green, one is going to be like that, and the other is going to be like that.
Okay.
So one of them is negative, the other is positive. I have to really think about who is who.
Right. So I was just confused about the data. I mean, delta has less information in the right hand side picture.
But there is delta check, which
Okay,
which is now 2-dimensional. So the amount of information is more or less the same. It's a switch delta and delta check.
Yeah.
So delta check.
Is it really hard to write the EF formula for just one of these cases? Like k equals 2, n equals 1. It's difficult. Like just the EF definition.
Yeah.
What is it?
Well, I wrote it. What do you mean?
No, but you wrote it for only the codimension 1 case, right?
It only
E
works.
tensor.
It only works. What do you mean? Codimension 2.
Sorry, codimension 2. Like,
Yeah. When you only have one loop in your monitor.
Yeah, so I see. So
There's
it
only one
needs
loop.
to work.
But here you have, the pi 1 is like has 2 loops. So you have a larger. It's not just one number. I mean, it's not just one loop. So you have a monodromy here, you have a monodromy around here, and then you also have a monodromy around here. Okay.
So this is more like this existence of these this simplices is more like consistency condition.
It's consistency of the monod, exactly. Yeah, exactly. So this is why I want to see this. So this is actually also tells how my monodromy move if I'm from a larger strata into the deeper strata. So that monodromy kind of stays in that neighborhood, and that stays there as a face of the larger simplex. Okay, everybody knows, of course, what the answer is, right? To the local model. Local model M is x0 xk equals 1 plus w0 plus, sorry, w1 plus m. So this is people who have been working on that a lot, of course, and so this is a hypersurface inside ck times ck plus 1 times c star d plus n, when d is no coordinates there, so d is just kind of free variable. And of course the question is, all right, so how do you construct a Lagrangian fibration from this guy into that base? This is not the way how we approach it, so we kind of approach it. So the idea is, okay, so this is a complex surface, hypersurface, and then you wanna put a symplectic form on it from the ambient space, and then you kind of try to do Lagrangian fibration. This is not the way how we do it. We kind of do it the opposite. We start with the hypersurface in a moment coordinates. Well, we start with a symplectic structure in this storic variety as a symplectic manifold, and then we define the equation of the hypersurface by certain potential. That's the way how we do it. So here you would start with a complex hypersurface. You define your symplectic form by choosing a potential, and we are doing the opposite. We are starting with a well-defined symplectic form here, and then we're defining the hypersurface as a potential. So that's roughly the idea. So okay, now it becomes a little.
And the two choices are relayed by those donor pressure.
If the potential is strictly convex, which is not going to be, so this is actually the key point I'm trying to emphasize. If potential is strictly convex, of course, there is the Legendre transform between, these two pictures are more or less the same up to making the Legendre transform. But our potential is not going to be convex. So we actually will not have a complex coordinates everywhere, only in some regions. Okay, so data. So all right, this is bear with me a little bit. There's a little bit of combinatorics, well, some polyhedral stuff involved. So we start with a integral space, 1 plus d plus d. Inside of it, we have a subspace n plus d. And then there's a map into the quotient. I'm going to call this quotient rk plus 1, the dimension. And inside of here, we choose octant, integral octant, which I'm going to call. So the meaning of this is like a colon over the well, yeah. So okay, so wedge here, the main object here, we're going to call it wedge because it looks like a wedge in my picture, which I'm going to draw. So wedge is the, so let's call this map Q. So it's a Q inverse of the positive octant. So the picture of the wedge is really the wedge. So this is the focus example. So k equals 1, n equals 1, d equals 0. So you project the guy into the over here, and then you. So it's not just the boundary of it. It's the boundary of the wedge is going to be our integral affine manifold. Okay, I will not say what the integral affine structure is, but maybe I'll. So I need more data here. So first of all, where is delta? Delta is inside. So my delta is going to be a simplex here. Let me draw it a little bit off the chart because it's floating, right? So I can put it anywhere. This is my delta. I'm going to add one more point to delta. Let's call it kappa. So kappa projects to the 1, 1, 1 vector. 1, 1. In this case, 1, 1, but in general, there are many ones. Okay, 1. What else do I need? I need also, now it's important part, I need a projection pi. So this is the data. So this is a choice. This is a choice. This is a choice, in some sense, it's more or less canonical though. Another choice is the projection pi. So projection pi is the map from the wedge into the Rn. So Rn I'm going to call the thing which is spanned by delta inside here. So there's a Rn. So the projection, so okay, I'm going to call sigma hat is the preimage of the 0. Let me draw the picture here. So you take this wedge and then you project down to this is Rn. Yeah, this line. So you project to this is a choice. It doesn't have to be integral, that's important. So the preimage of the 0 is going to be some sort of cone. So this is, and the boundary of this cone, I'm going to call sigma. So this is the boundary. So this is sigma, and this is okay. I'm not gonna, okay, I mean, let me skip the integral affine structure, but it's sort of very, very simple what's the integral affine structure. So on the boundary, how can you imagine what the integral affine structure is? Well, each flap of the boundary has its own integral affine structure, because it's an integral subspace inside the integral space. Now the question is, what do I do, for instance, on this side of the discriminant is given by this sigma. Maybe I should say discriminant here So this is the boundary discriminant is the sigma. Let me call it 1. It's a codimension 1 fan in sigma cross what I'm gonna call this fan F. So there is a fan F transversal. This is, yeah, I forgot this choice also. So there's a fan F also, which is transversal to delta. So maybe in dimension 2, I'll draw the picture. This is delta, and the choice of the fan is it's a choice again. It's a uniformly transversal fan F. And I take the again the dimension 1 skeleton. My discriminant, and the coordinates, for instance, on this, they come from the projection along this vector here. So I take the vector from kappa to the corresponding vertex of the delta and project it, and that tells me what's the affine coordinates on this banded thing. So I look at the banded thing. I want to see what's the how do I visualize this at an integral space. I look at it at an appropriate angle, and that tells me what's the affine coordinates. And the angle is given by that vector from the kappa to the vertex of the delta.
What is the upper index 1? Sigma 1 cross F1.
But so it's a codimension 1 skeleton of the fan. The fan is full dimensional, and then it's I take the codimension.
Yeah, sure.
So in this case, for instance, for the fans are both one dimensional. The codimension 1 is just going to be vertex times the vertex. It's just a single point.
You mentioned that the point above your delta is the choice.
It's not, well, it's not very, I mean, this choice is sort of only relative to this sigma. But this is the integral point. This is important. This is the integral point.
But I can sort of move it.
You can move it, for instance, over here. But then you would also have to kind of simultaneously move the sigma.
Okay.
Yeah. Otherwise, you would get a different picture. Different. I mean, in this case, you're actually not going to make any difference. But in the next dimension, you would actually see the different position of the discriminant. Okay, now comes the main player here, which I'm going to call the hypersurface. So before I define the hypersurface, I'm going to define the potential first. Potential is a function capital phi from the wedge into the reals, convex. As I said, I do not require strict convexity. And it has to have appropriate behavior near. So let's call this coordinates here V0, Vk. Then I pull them back, call them the same name, V0, Vk. And then it has to be 1/2 Vi log Vi. So if you know anything about toric geometry, that's the necessary shape of the potential. You have to be able to compactify the metric to the bound. Plus some smooth function. So once I have this convex function with that behavior near the boundary, I'm okay. Now, of course, yeah. So the Liouville form is let me call it like d theta u plus v d theta v. So pretty standard form on around the space. So as I said, so on c to the k plus 1 cross c star n plus d.
So T
Yeah, there's a t also. But I'll put them all into a u. So I didn't say what's the t coordinates. I only said what's the v coordinates. The u coordinates are kind of along the Rn, and there are also t coordinates around the. So this is the coordinates in a rd direction. So this is in Rn, and this is in R k plus 1. So I have this is again a choice, but the form doesn't depend on the choice.
And when v tends to 0, that means you're approaching this sigma, or
Yeah, I'm approaching the yeah. So like if you know, like for instance, what's the metric on cis square. How do you write your potential on a toric in the coordinates, in a moment coordinates, right? So it has to have this behavior to go all the way to a smooth metric.
And sigma here is somehow replacing the toric boundary.
Yes, this is the toric boundary. It's not just a sigma. It's the actually this is the entire boundary. So like everywhere on the boundary, I have to approach with that behavior. Okay. Now the hypersurface. So I'm ready. Are you ready? So e to the partial with respect to, okay, so I'm gonna maybe use some notations here.
Are you ready, really?
So this is simplex delta check, and though there are vertices A, B, maybe a bunch of vertices, and there is a special vertex kappa which projects 1, 1, 1. So I'm gonna code actually maybe the other way around. No, it's actually correct. The vector from kappa to A as a hat, and I'm gonna So this is B hat, for instance, and I'm gonna. So this is a vector, well-defined vector in the tangent space. I can differentiate with respect to this vector. So let's call it A hat. My potential. Then I add the corresponding dual theta coordinates. Okay. And then I put some cutoffs here, depending on A, and take the sum, and that has to be equal to 0. Oh,
Sorry,
1.
Sorry, is this a delta hat? This blue triangle?
The big one is delta hat. The base of it is delta.
Oh, it's a delta hat.
I've introduced
okay.
introduced one more vertex kappa.
Okay, and then the B, I misinterpreted this. So the B is actually the dot on the right, the little b.
The little b is dot. Yeah, so the little b is a dot here.
There's another choice here.
No, it's not. This is so. I'm going to take the sum over all possible vertices of delta. A in vertices of delta. So for every vertex, I take my partial derivative with respect to that vector, and I put it in an exponential.
I thought about the little b. Where did this come from?
Little b.
Yeah, is that that's a b, right? Yeah, what is this?
This is b. Let me call it A prime. If that confuses you. It's just a vertex of the delta.
Oh.
And the vector from the top is
Sorry.
to that
Yep.
vector.
Okay.
A prime. Okay, that's not 0. It's 1. Now, of course, okay, you see this one, you see that one, everybody see that it's the same thing, no? It is, except you have to put the rows here, of course. Row 0, row 1, row n, and then you have to make a choice of the coordinates, and the choice to make of the coordinates. So if you choose a delta to be the standard simplex, namely that you have an origin here, and this is like this. So this origin is 0. This is 1, 0. This is 0, 1. And then you also have kappa to be, kappa has several coordinates, but so it's 1, 1, 1 in a v coordinate, but it's all 0, 0, 0. So it's like strictly on top of the. So it's like that. So it's strictly over the vertex 0. If you change this, if you take these coordinates, then you actually can. This is the same thing. Okay, 10 minutes. Good. Okay.
What was the row A?
Row A, I didn't say what's the row A, but the row A's are meant to cut off some of the monomials when they are already small. This is like this this is a typical, what people do. There are different names to this. People call it like a Gamage-Nadler, call it tailored hypersurface. Abu Zaid called it like, huh? No, Abu Zaid did not call it. I think Abu Zaid called it almost tropical or something like that. I mean, there are different names for it. We call it actually. We have our own name. It's called ironed. Because tailored is you have to saw something. But the point is that when Cheuk probably showed the pictures, like if you really, for instance, like in one dimension, if you see, it's really like a flat thing, and then there is some blur thing in middle, and then it's again flat. So it's flat in most of the cones. If you look at the moment map of this hypersurface, how it sits inside the wedge, it's really like a this flaps.
When you draw the amoeba and the plane, standard amoeba, the iron,
Yeah, this is the one.
then it doesn't look like that.
It looks like that, yes.
Well, if you compactify, don't you do compactify.
It's in a wedge. In the wedge, it looks like that.
You know, the standard amoeba picture, and then you just make the unbounded pieces straight lines.
I don't want to do that because that's
That's the
using the complex coordinates. I'm not using the complex
Yes,
coordinates.
but that's
There
people,
are-
people understand. Okay?
People understand. If I'm using the complex coordinate, then I would see something like if I'm this picture would look like if it's
You can draw the same picture in the moment, inside the moment polygon.
yes, that's a picture inside the moment polygon. That actually makes sense.
I think maybe
Where's
can
moment
we do it in the two dimension?
Which dimension are we at? 2? What?
Like two moment map of the CP2?
Then my wedge is going to be
Yeah, nobody understands that.
Yeah, like this picture
Okay.
is not very understandable.
I don't know what this is.
It's you take the amoeba in 2 dimension, compactify one of the unbounded guys, and get this funny thing.
okay. I'll do, okay. So I'm gonna draw this picture in CP2.
I think we want both of them.
Both of them. All right. So let's draw. So in the log coordinates. In log coordinates, which I do not have. I'm emphasizing it like third time already. I do not have.
The other one, why not? I mean, I don't know why.
In the log coordinates, the picture of the amoeba would be something like that. That is without rows. With the rows, the picture would be like that. So it's really like flat. There is no thickening here. And in the moment coordinate, that picture would be like that. So this is when v equal to 0. It's like that. Then it's sort of some blur, and then it's really flat. So it's I mean that thing compactifies to 0, right? Because I'm compactifying not to CP2. I'm compactifying it to C times C stars. So that's my C cross C star. So I compactifying I'm adding only one line here. That collapses the whole thing, and these two things become actually horizontal.
Yeah, that's very important.
That's important. That's what I want. I didn't say how I'm going to achieve it, but my potential will have this property.
So you distinguish some directions.
No, that's the point. I'm not distinguishing the directions. They're all flat.
There.
So that would distinguish some direction, yes. But this is the good thing.
Where's the third tentacle?
It collapses because I'm compactifying. I'm from this
Yeah,
is
so-
in C star squared that would have this, but when I add line
Right.
at infinity, that thing is gone.
Yeah.
So
So
there is just
Yeah,
it adds 1 point.
that's what I meant by distinguishing something. Yes. Okay. But
I'm
no,
distinguishing,
you
yeah.
don't. You don't. Yes.
I actually do distinguish which way I
Yeah.
compactify.
Yeah.
Okay.
That's 3 years of work.
Yeah, I don't know why is it supposed to be.
And we are supposed to understand
I'm
it in
gonna
30 seconds.
explain. I'm gonna choose the potential such that
That's the magic of the potential.
that's the beauty. This is the key thing. So I want it to be like that. And for that, I'm gonna choose a potential so that it has this shape. And let me explain now what's the condition of potential.
But I'm still may I still point out my point. So for this negative vertex,
Yeah.
you do have the 3 tentacles. So
That's a picture not for the. This is actually a stupid picture for the like one x equal 1 plus w.
I see.
If okay, well, you want to draw me in negative vertex, I probably won't succeed. But you have a
Then
so
I see.
you have a plane
Uh-huh.
compactify, and then you'd have this. Actually, it's not even a negative vertex. It's the one which is. I'm drawing it. Let me draw 1 plus w, 1 plus w2. It's not even a negative vertex. It's a stupid case. It actually has a stupid torus fibration. But the picture is sort of you're trying to. You have like a well, I'm not going to succeed, but
You have some blob coming out or something?
yeah, there's a blob in the middle, and there are like, you know, this
Yeah, okay. got it.
three flat flaps, and then there is also some blobs in between the flaps. So when x equal to 0, you would actually see, you know, this picture over here. So on the bottom, you see this picture. Well, and then on top of it, you see some numbers. Okay, so now let me say how do I achieve this? And this is actually the key point I have 5 minutes for. But, well, Cheuk Yu. Sorry. So, okay, so I'm gonna do with behavior. So first to think, okay, my potential is going to be in the form. I'm gonna have some function which is pulled back from the v coordinates. Let me call this function little psi. And then there's a pullback from the u coordinates, which let's call it phi. So psi is a function on r k plus 1 bigger than 0, and phi is a function on Rn. Let's set equal to 0. So okay, and the behavior I want is the following. So first of all, phi. Let me say so. Okay, I'm gonna do the covering of my rk plus 1, rk plus 1 bigger than 0, and the covering I want sort of cut some neighborhoods of the boundary. So this is v0, this is v1. And what I want, of course, I want the behavior into that direction to be, you know, log 1/2 log. This is v1 equals 0, so it's log v1 v1. So that I want. So that if you've seen the function, this one it looks like this. So it starts at 0 and it's very, very convex at the beginning, and then it starts growing like that. That's the function. Yeah. The point is that it's very convex near 0, like infinitely convex. That's good. So I want a lot of convexity in that direction, but I want linearity into that direction. So my potential is going to be linear in some directions and convex into the other directions. So this is linear. If I'm far away from here, so linear in V0. That's sort of what kills my non-degeneracy of my metric. So this is where I actually do not have a complex coordinates. But why do I need? So that actually takes, and maybe the picture, I'll draw the similar picture in Rn. The similar picture for this function. So this is for the function psi. So that's what I want. And in Rn, I want a picture. I have my fan f. And I want the covering I want is, so this is where the discriminant is going to be. So I want to cut the discriminant a little bit. Yes. Neighborhoods. So first of all, in this region, I don't want any functions raw except, so all these things go to the thing. So this is A, B, C. So this is FC, this is FA, and this is F. B are the maximal cone of my fan F. So in FB, I don't want any row except the B to be here. So and every A not equal to B is 0. So that's I cut off all the monomials except the monomial which correspond to here. So this is about the rows, and the condition for the phi. This is psi, and this is the phi. For the phi, I want again. So I want convexity, very convex, but in this direction I want linearity. Let me explain. So what I want, the linearity I want. Okay, so let me make a final statement maybe, and then I'll say which part of this properties is used for which. Convexity is used to prove symplectics. I need some convexity. When I have more than one, I need passing from them. If I have two monomials here, I have monomial C and monomial B, and if I want to have two monomials in my right-hand side here, I want them be close to being holomorphic. So that's the way. This is a Donaldson's trick. Cheuk Yu will say more about that. So if I'm holomorphic, I'm symplectic, but if I'm not too far from being holomorphic, I'm still symplectic. For that, I need convexity here. And I need my linearity for certain behavior of this hypersurface in certain regions. In particular, let me call this region, well, 2 minutes, is that okay?
Yeah, I think so.
So let me maybe 2 minutes. So let me call this region, let me just do an example. So this is tau, so this region is u tau, and let's call this, so for every sigma element in sigma, I'm going to call this region V sigma. So in V sigma is when Vi is bigger than some number for all I in sigma. And I'm not going to define what's u tau. So u tau and V sigma, the behavior I want is the following. So in, well, so first, so proposition. If I have this behavior, then first of all, M is symplectic. Second statement, and in, right, mu is my moment map. So mu is a moment map for my toric variety, C K plus 1 cross C star plus D into the wedge. Mu inverse of this neighborhood, U tau cross V sigma, or maybe pull back to them into the wedge. I have the following thing. So I have a certain torus action. Hope Cheuk Yu will explain which one. So, and I have also the invariance of the. If I look at my potential, my hypersurface here, anyway, okay. So if I look at the partial derivative of my potential with respect to nu for any nu sitting inside sigma cross f tau, so in that direction and in that direction, in any of those directions, I want that to be constant. And then the conclusion is that if I apply any of this to the equation of the hypersurface, nu is invariant. So I have torus sections. I have invariance. I have certain number of tangent vectors in the ambient space which are tangent also to the hypersurface, and that and it's symplectic. And that, in fact, is all I need actually to run the Evans-Maury flow. But anyway, so just to emphasize, so this is a very sort of little subtle things we will need. Just need one function with certain properties, and the function and the fact that the properties will need convexity and the linearity, and we can actually make this function because the convexity we need is in a perpendicular in a transversal direction to the directions of the linearity which we want. So, and that's maybe one final.
So how did you define M?
By this equation, as is M.
Equal, I see. That was equal. Okay, sure.
Claim 80% theorem. Any hypersurface in a smooth toric variety has this. We can apply this run it for has this Lagrangian torus fibration. Any anti-canonical.
80% of this state.
80% true, I would say. 80% true. 80% theorem. It's about 12 hours old, so maybe. But we're pretty sure we can talk. This is what we wanted, right?
Yeah.
I think yesterday we came up with like a final argument that we can actually make a global potential on the entire.
Yeah, that's what I was just about to ask you.
Yeah. We can make for this case we can make a global potential on a
Yeah, because
polytope.
like, okay, so maybe the talk is over.
Yes, thank you.